Video 3, Comparison Tests. In videos 1 and 2, we introduced the comparison test and examples. In video 3, we're going to look at the limit comparison test. Let's start by noticing that the comparison test is finicky. Looking at this series, we might want to conclude that it converges. That's going to require comparing with another convergent series. But the convergent series we want to compare with would be the larger termed associated sequence. Starting with n squared minus 1, strictly less than n squared, taking the reciprocal, we see that this inequality is going the wrong direction. Hence, comparison tests can be rather finicky. Less finicky is the limit comparison test, LCT. Like before, we want to compare two series which have associated sequences of non-negative terms. New to LCT is this notion of rho. Rho is spelled RHO and reminiscent of the ratio from the geometric sequence, but it's the ratio of corresponding terms, AN and BN. We're going to have three different statements for LCT. Here on the first slide, we'll look at the first statement. Let's see what it says. If we find that the limit of the ratios is a positive finite number, then the behavior of both series is the same. Either if one is converging, then the other will converge. On the other hand, if one diverges, then so does the other. This happens when the limit of the ratios is a positive finite number. Let's see why that is. So if the rho is positive and finite, then this sequence of ratios after some index is going to be basically equal to rho. That's the whole idea of a limit, that this quantity starts to look more and more like that fixed quantity. Taking this approximation and solving for the numerator, we get that an after some index is basically a constant multiple times the bn. Considering the series given by an's, to find its behavior, we look at partial sums. Take the first n minus 1 terms, and then consider all terms after the nth term up to index k. And these guys here behave just like the sum of the bn's from n up to k multiplied by rho. So the behavior of this sum will be directly tied with the behavior of that sum, since they're basically multiples of each other. Hence establishing that if the limit of the ratio is finite, then the behavior of the two series is the same. Good. Let's go on to the second statement. In the second statement, we're assuming that the limit of the ratio of the terms is 0. Well, an is positive, bn is positive, and we're finding that after a while, they start to look more and more like 0. So instead of looking out to the right, if we look back to the left, we can see that the terms of this sequence will be bounded. Suppose they're bounded by m. Then each of these is bounded by m. We can then write out that an, the numerator, is that bounding value times the denominator. Now we can think back to the comparison test. So if we have information on the upper term that it defines a series which converges, then the smaller valued sequence also defines a convergent series. Nice. So if the bn's give something which converges, then the an's will give something that also converges. Fantastic. One more. Now we're going to assume that the limit of ratios goes out to infinity. That's going to tell us that these ratios become arbitrarily large. In other words, they're unbounded. Thus, if we pick any value capital M, we can look far enough out in the sequence of these ratios and find that the numerator will outstrip the denominator by this amount. So now, if we take that the bn's determine a divergent series, that's going to force the series given by the an's to also diverge. Notice we're again relying on the comparison test. Thus, we've shown the three statements of LCT. Which is less finicky than CT? Excellent.